Yo, what's up, everybody? Welcome back. Today, we are working on our code visualizer, and today's topic is trying to improve render performance. So, let's launch our code visualizer, and we can show you what we're doing here. So, this is our code visualizer. I apologize. Let me know if the stream starts to lag a lot. It was lagging a lot the other day. But what we are rendering here is each node on this graph is like hold on, checking my frame rate again. Yeah, it looks fine. Each node on this graph is like a function, file, like type, folder, like any like part of a code base. And we are trying to visualize as we act on certain parts of the code base, like edit as we're like working in the code base, how much of our time is being spent in some area, and can we like visually represent what subsets of the code base we're working on in a given stream. So like for example, if we're working on like the text renderer, we should be able to like crank up the visibility of like the sections of the that are related to that thing, right? And so what you're seeing here is you're seeing backgrounds for certain areas of this thing that are kind of based on where the things are located, right? So if I hover over like this section here, all of this stuff is in the text renderer in the class layout helper. If I look at this like orange section, this is still text renderer, but now we're seeing like, oh, this is maybe in like different functions within that thing. And the way we're drawing these backgrounds is we are going in OpenGL, we're saying for each pixel, basically try to figure out which object is closest. And the way we do that is, I'm just going to close this so that we don't have to eat that like render cost over and over. But the way we do that is essentially, for each point in our graph, we draw like a cone, right? And we look at that cone from up above. And what happens is this cone has like an ID or like a color associated with it, right? So this cone will be like yellow. Maybe I'll just write Y here. And we draw another cone next to it for another point, right? And this cone is blue. And what happens is you end up getting like a line kind of going through here of where those two cones intersect with each other. And OpenGL, because it's like a 3D renderer, will like automatically sort those things and like figure out which one is on top and which one to draw. That's the idea here. You can see we do this in like multiple passes. So if we like open render doc, we can see like we start with like the lowest level and we like work our way up, increasing in saturation as we get up to the highest layer. But the problem is this is like insanely slow. We're seeing like, look, this is saying like color pass taking 32 milliseconds. That's crazy. 32 milliseconds is insane, right? That's like what we're at like 30 FPS or something, and like what are we drawing? We're drawing like 1,020 vertex polygons. Like what is happening? What is happening there? Because like I can render like full games with complex lighting at like easily at my monitor's refresh rate. And so today's task is to try to like get these render times down. So I've been doing some reading, and I think I understand at least like some of the causes here, but definitely not all of them. So I think we're gonna just like start with like fixing the depth prepass. What's supposed to happen, I'm pretty sure, is that like we're supposed to be ensuring that each pixel is only drawn once. I'm pretty sure that's not happening. And then there's a lot of like, even I think after we fix that, it's still gonna be quite slow. And so I think that we just have to like start tackling it from whatever angle we think is most appropriate. I think we just have to poke and prod and start moving. So let's do that. I'm not entirely up to date on the project, but do you know if there's a lot of subpixel triangle rendering? Oh yeah, you're talking about like quad overdraw, right? You're talking about the thing where like, it's like you have like a long skinny triangle, and if this is like kind of taking up, I think that like they do batches of 4 pixels at a time on the GPU or something, and so like what happens is if your triangle goes through like one of the 4 pixels that are being rendered, kind of like it's only hitting this one, you're wasting time on all of these. I assume that's what you're talking about. I don't think that's our problem, for reasons that we'll like get into later. But it is worth considering for sure. Okay, the first thing I want to do is I want to fix the depth prepass. So if we read like OpenGL pipeline, and by read, I mean go to the OpenGL wiki, because I ain't reading no spec, which is probably stupid, but I also don't like know where I would even do that. they kind of talk about how you go through like these stages, right? So we hand wavy set up like the vertices for our cone, we stick them in some memory somewhere, and then we set up these extra memory for like let's offset this cone to these locations, right? And we will then like try to figure out the shape of those cones by running our vertex shader, transforming it like so you can like rotate, you can scale, you can like offset, all of that stuff. What happens then is each fragment that is processed is sent to our fragment shader, which basically like says like I'm going to color this thing in with according to these rules. And somewhere in here, they talk about how depth. Where do they talk about like depth testing here? Here, yeah. So after in the like official spec, after you calculate the fragments for every single one of the cones that we draw, it then decides which fragment was on top, right? Because like if you draw like a bunch of cones, we draw like a cone here, a cone here, a cone here, a cone here, right? For like this pixel, only one of the cones was on top, right? So after it's done all of that things, it goes like, oh, which one's the best? Up to the top, we'll use that one, right? According to the OpenGL spec, I'm pretty sure they say that like the depth test is supposed to happen after your fragment processing, i.e. after your fragment shader is run, i.e. for every pixel. And by for every pixel, I mean probably like for 4 times every pixel when we have like multi-sampling / anti-aliasing enabled or whatever. But you can they can come before the fragment shader, which is very important because it means that you don't have to run your like per pixel program for every cone. You only have to run it for the one that was on top. And if you read this like this thing, I think they talk about like discard in here. Yeah. If a fragment will be discarded based on the depth, no, not there. Here we go. If the fragment shader discards fragment with the discard keyword, this almost always turns off early depth tests on some hardware. Which we are doing. So we can just fix that really easily. Let's background this render doc. And then just go into our like fragment shader for this thing. And here we're doing like if depth is greater than some threshold, discard it. And I'm pretty sure that if we just change this to like float alpha is equal to the same thing, this is now going to be 0 alpha or 1 alpha. Instead of discarding it, we just make it invisible, which you would think would be slower, right? You'd be like, wait, this should mean that like we have to do more processing on these things. But it turns out that this allows the depth step to run early because the outputs of the fragment shader like are not just the color, they're also like you could adjust the depth in here. You can like fuck with the depth texture from here. And so like the discard keyword says like, hey, like you can't know what the depth is going to be because I might do something special here. I might dodge writing to the depth buffer here. So if we build with this and we rerun, so let's just keep an eye on this number. We'll say initial frame time was 32-ish milliseconds for full pass, and approximately 16.8 milliseconds for first level of Voronoi. Yeah, okay. So we build, we run, and we capture again. And I believe we should see like a pretty big improvement here. Yeah, so we go down to 12 milliseconds from the 33, and our first pass is like 5.2 instead. So that's like a pretty big win just from like deleting that discard keyword. And if we like look at the content of this thing, this looks still pretty reasonable, right? I think this is still doing what I would expect it to be doing. In some ways it actually looks kind of fucked and weird, but I think that it always looked fucked and weird in those scenarios. So I think we're good. Okay. So that's step 1. Now the question is why is it still taking so long, right? I would not expect this amount of slowdown for something so simple, right? Let's look at this again. Sorry, we'll capture 1 frame. Take a little peek at it. So here we're still seeing like 5 milliseconds to draw this, which again just feels like a lot to me. I feel like we should be able to do much, much better. And so I was like Googling around a little bit about like how to do like OpenGL performance testing. There's this like AMD utility I could use, but I couldn't get it to run on NICs, which is a little annoying. I should try that a little bit more later, maybe. But for now, I think that we need to like bisect where the slowdown is coming from, right? We have some options. It could be in our like vertex processing, right? So we have like 20. Here we see we have 20 vertices per cone. We're instancing 1,000 cones. Is it just slow to do that, right? Maybe that's just slow. Irrelevant of how many pixels we draw after, maybe our pixel drawing is very fast and it's like the vertex processing is slow. Or maybe it's that the vertex or like the fragment shader run is very slow and the vertex processing is really fast. So I think I saw in like this, I think I looked up like OpenGL benchmarking or something. Performance testing maybe? Here, performance. In here, they say some stuff, but pretty much the main thing here is a really simple test is to reduce the size of the window you're rendering into the size of a postage stamp and see if the frame rate improves. If it does, then you are at least partially fill rate limited. If it doesn't, then that's not a problem. Such a simple test should always be the first thing you try. So basically they're kind of saying like, if you make your window really, really fucking small, you still have to process the same amount of geometry, but you have to process a much smaller amount of pixel data, right? Which means that your fragment shader needs to run way less times. And so if your performance heavily improves, you're likely at least somewhat limited by the speed of your fragment shader. I think that's what they're saying. So we can try that. We can try that. We can go to our viz zig and take our window size. Window. Here. And can we just like drop this shit down? Also, while we're here, actually, I kind of want to make sure that we're only kind of doing the first bit of the loop. So let's do this. If true, we say glw gl swap buffers and continue. And then here I also think we have to make sure that we're draining our input queue. So I think it's like discard however many things are in here. Okay, so let's just quickly run that and make sure that we're getting what we expect to get. Okay, cool. That is what I expect. You know what? Yeah, it's fine. It's I'm actually like a little less convinced about some of these things. I mean, these lines down here are looking pretty strong. Okay, cool. So we'll just keep going. We'll keep going. We'll assume that things are working correctly. Actually, I'm not. I just want to go back to that discard thing, just to double check if it always looked like this. Because I'm noticing some like hard lines in there that I feel like look kind of weird. Oh, but there were always some like that. Okay, cool. It's because we're rendering in different layers, which is like kind of fucking stupid. But that will be addressed later. I have a fix for that in mind. Okay, so we are running successfully, and we're only running the Voronoi section now. And so now we can really like clamp down this window width. So we can kind of ditch this sidebar concept. No sidebar necessary. And then can we take the window width here and drop it down to like 500 by 500? Just to make sure that like, everything is working the way I want it to. Okay, so it looks like we are still getting this thing here. And if we go even smaller, 200 by 200 or something, crank that down. Okay, so now we have like way less pixels processed, but the same amount of vertices, right? So we're doing the same amount of vertex processing, different amount of like pixel processing. And what is like the difference in our behavior now? So now I hit capture frame, I hit go away, and we look at the render times here, and we have dropped a lot, right? We've gone down from, what was it, like 5 milliseconds here, down to 500 microseconds, so 0.5 milliseconds. Which is a big improvement, right? So we can make the assumption here that there is at the very least some amount of fragment shader slowdown. But I would also be curious to know if we kind of like undo that test, right? And we go back to our 800 by 800 window, I think is what it was like before. Oops, I didn't mean to close render doc. One sec. Launch. Sorry. Launch. We go back here. We replay, or sorry, capture frame. Look at its timings. And we are back up to like, yeah, 5 milliseconds here for this first level of Voronoi. And then I wanted to try, what happens if we like really reduce like the number of elements that we're going to render here. So let's say that we only render like 10 of the cones instead of 1,000. So something like this. Something like this. So if we like heavily reduce that, now we see only a few cones, right? We're seeing, oh, I don't think that we ever uncapped our frame rate here. So I think that this frame rate counter is not a good indicator, but I think that probably the timings in render doc probably are. Yeah, so here we also heavily reduced our render time from like, what was it, 5 milliseconds down to 0.2 milliseconds. So somehow both the number of vertices and the number of pixels drawn is causing mega slowdown. But here, I mean, we're only drawing a few pixels here, right? So let's make sure that, oh, fuck, I didn't mean to close that again. God damn it. Let's make sure that we can force this thing to kind of fill up as much of the screen as it wants. So we're gonna, I think that there's like a lot of like 0 alpha stuff happening in here. I'm pretty sure. If we run this again, we should see the whole screen get filled, which means that the fragment shader would be run for every pixel, which means that we can get a, yeah, here. The whole screen is filled, which means that our fragment shader running on this code is running for every single fucking pixel. And I think that here, we still see a big performance improvement, I think is what I saw before. Yeah, so here we're still seeing like 0.3 milliseconds. So kind of strangely, we're seeing both reducing number of instances and reducing the number of pixels heavily improves performance, right? And so I think this means that there has to be some amount of heavy overdraw happening. It has to, right? It means that like something is drawing stuff behind that it doesn't have to draw. And I don't really understand why. And so that's what I think I want to look at next, is try to figure out like, why like where is overdraw coming from? The cones are big and most of them overlap, so it overdraws that, question mark? Yeah, let's look at the like the 3D render of this thing. We have an example from yesterday when we were looking at our GLTF export here. We can kind of get a feel for like what type of dumb shit we're doing here, right? This is kind of what we're doing, right? We have like a ton of cones, and we're only seeing like a small portion of each cone, right? So we could make an assumption here that like they're being drawn in like some order, right? We're going cone, right? And like you could maybe guess that like, I don't know if like shading is done on like a per triangle basis, right? This is kind of like what one of the triangles would look like, right? So you could maybe say that like maybe we're drawing full triangles for things that we shouldn't. That's one option. I don't think that's the case from what I've been reading. It seems like fragment shader, like the depth sorting of like fragment shader stuff is run on a per fragment basis. RSE render doc can show overdraw as an overlay in the texture view. Could be helpful. Yeah, it does sound helpful, huh? Because that was something I wanted to look at for sure, overdraw. So I think that we could maybe try bisecting. I read somewhere that you can completely disable the fragment shader in some of this like early Z fragment test stuff. The most effective way to use early depth test hardware is to run depth only pre-processing pass. This means to render all available geometry, including using minimal shaders and a rendering pipeline that only writes the depth buffer. So we click this and we figure out like how to disable color rates essentially. The vertex shader should do nothing more than transform positions, and the fragment shader does not even need to exist. So I think what I want to see here, if your triangles go below 2 by 2 pixels, you're gonna have a bad time. I don't think that's what's happening here. I think that you're right about that. I do not think that's what's happening here. I think that like we're seeing something like way dumber. Okay, so what I want to do is I want to completely disable the fragment shader and try to do a depth only prepass and see how fucking slow the depth prepass would be, because I think that will give us a clue into like what to look at next. So I think that let's read this thing. Right mask. So you can like disable color, disable stencil, disable depth. So presumably we run GL color mask, disable writing of frame buffer color components. So with I, you're probably picking like which color buffer. GL color mask is probably all of them or something. Can be used to mask all draw buffers. Yeah, so I think that if we just go in here and we say like GL color mask, was it GL false for all 4 components? Something like this. We should see no more color come out. And then we should also disable our fragment shader as well, but let's just make sure that like if we run this, yeah, we see no color. And if we capture the frame and look at like the depth buffer that comes out of this thing, I think that our depth buffer that's being drawn is still saying, oh, we should probably crank up the number of triangles again. Fuck, I closed render doc again. I keep fucking forgetting. Let's, yeah, render them all. Okay. So load last, launch, capture, wait, we look at the thing, we hit the time button, and we see, yeah, this is still taking on the order of 5 milliseconds. We see that the color that comes out is like total fucking garbage shit show, who cares? And I think that the depth buffer still kind of looks like a sane Voronoi pattern, right? We're seeing each cone here is like running into each other, I guess. The cones are smacking each other. We're seeing like the pattern we expect to see, right? So my suspicion based off of this is that I guess wait, hold on. We still need to like completely disable the fragment shader just to make sure that it's like not running. So we can go into our node Voronoi here and compile link program here, takes in a vertex shader and a fragment shader. He compiles the vertex shader, he compiles the fragment shader, and then he attaches them both to the program. So theoretically, we can just comment out the fragment shader stuff. Maybe we make it optional. Maybe we do like you can choose not to pass in a fragment shader, and then you say like if fs, maybe we call this fs opt to prevent name collision. And we say if there's a fragment shader, compile that shit and link it to the program. Otherwise, you know, don't. Okay. So now we can go into our thing and we can put null for our fragment shader. And oops. Let's run this thing again. Okay. capture frames, bing, bang, boom, and hopefully we still see something a little reasonable come out of this thing. So we hit the time button, 4.5 milliseconds, and we still see that the depth buffer that comes out of this render is like sane. And now we know for sure that like we should not have a fragment shader tied in here, but the vertex shader is our vertex shader. Our vertex shader is outputting a UV position, which seems kind of silly. I don't think that we need that. Why don't we just like fucking like nuke that? Why don't we like nuke a lot of stuff from here? If we have no fragment shader, can we just like disable propagation of this stuff and just kind of see what happens? Can we just delete a bunch of output or output parameters and input parameters? Like, can I just do this, apply changes, and can I like hit this again, and does it? So he's not happy there. I guess that's not good. Reset. Apply. Okay, so our buffer is still there, and then we come in here, and can we just start like deleting shit and see if we can like get it to stay? Okay, what happens if we like do like times 10 here? I just want to like be convinced. Yeah, this does seem like it's definitely taking effect. So can we just like delete our output parameters here? Like, does that still work? And then if we rerun this, ooh, okay, that's kind of interesting. That dropped our time a fuck ton. Like a lot of that, like a lot. Assuming that this was correct, right? We go back and we reset this thing. And we apply changes and we hit this button again. We're back up to 5 milliseconds. So which one of these things did that? Drop the UV, apply, run. That one's the same. Drop the distance threshold, apply, run, same. Drop the color, apply, run, same. Drop the depth output, apply, run, same shit. Okay. Drop the distance threshold input, apply, run, same. Drop the color input, apply, run. What the fuck? Am I high? Didn't we just see this have like a mega effect doing the exact same thing? The multiplying did it? Oh, yeah, that's a good point. Did it times 10 here, right? Apply, run. Yeah, okay. Which kind of makes sense because we're probably, all of this stuff on the outside is getting like washed out when we do that. So that's kind of like the equivalent of like if we took like all of these guys and like scaled them in Y, we're essentially doing this, right? And probably what's happening when we do that is like a bunch of parts of these cones end up outside of the view frustum. Like there's like this like box, right? This like 3D box that we are rendering in OpenGL land, right? Like we can kind of probably show it in here if we take like a cube, right? We can kind of imagine that all of OpenGL stuff is happening inside this box, right? And probably what we did by stretching out all of that stuff was we probably like took some parts of the cones outside of the box like this, and we probably lost some of the render, right? You can kind of tell that by looking at like all of like the white segments in here, right? If we like kind of like come to here, everything past like this point, all of the stuff in white just wasn't rendered anymore. We have like a pretty good inkling. I don't know if I'm like positive about this, but I do not think that we are writing to the color buffer, right? We disabled that, we turned that like GL color mask thing off, right? So my best guess at this point would be that the writing to the depth buffer itself is causing us pain. And we could guess that every cone is serially rewriting the entire depth buffer. right? Because each of these cones is like a fat motherfucker, right? Each of these is taking up like maybe not the full field, but maybe like a quarter of the field of view, right? I think it's supposed to be designed so that it takes up the full thing, but we might have like fucked it up a little bit. But you can, these things are like big. Oh, actually, I think that in this example, actually, that this came from, the viewport was actually supposed to be kind of like this. Yeah, so each cone fills the entire fucking screen, right? And so if you draw cone by cone, if you drew them in order, you would start by filling the depth buffer with the output of one cone. Then you would rewrite all of the depth for any of the parts where it sits on top. Okay. I think that's right. Right? Right, so we start by like, we start with like all but one. Then we add a second, then a third, and that ends up writing like, your first one would write like this whole area. Then if your second cone goes here, basically we find this intersection, and everywhere on this stuff is like more. Yes. Then we like take this one, and basically anywhere, if we drew another cone here, anything in this section would get reshaded. But like, surely that's not actually that much, right? You would think that after you render a few cones, that the amount of increase of the like amount of increased time per cone, I would think would go down as the screen fills up, right, in this model, because every cone would only rewrite to some portion of the depth buffer. But maybe maybe you have to pixel test. You might have to like, you still might have to like render, like interpolate the depth for each triangle at a given depth, and then figure out after that, like, you might have to do almost the same amount of work, just not actually write out to the buffer for every cone. Yeah. I mean, that's like not insane. That's not insane. So is there a way we can prove that concept? Can we prove that? We could make like a dummy app that renders a single plane and does that, like, just stacks the same plane on top of itself over and over and over and over and over and over again, and compare that to the performance of if we draw them front to back. Right? Because if we draw them front to back, then like the ones that come after shouldn't have any impact on the depth buffer because they immediately fail the depth test. And we could probably do this with a single triangle. Yeah. Yeah, let's try that. Let's try that. Because that will point us in the direction of if we need to fix this. And I have an idea of how to fix this, actually, that I already want to do because it will improve the render times in a different way, right? And we might as well talk about that now. So something that we are doing here is we are kind of walking up a hierarchy, right? And we're doing this like slow ass fucking stupid dumb fuck render, like not just one time, but like 8 times or something, right? Because we're saying like for the entire code base, render these like as one folder. Now take its subfolder and render that, and each of its subfolders render those, and each of those subfolders in there, or for each file in that thing, render that, and for each set gets like farther down this tree of shit. And I was thinking that like technically every point in the first render is like enough. How do I say this? How do I explain this? Okay, so like we have these groupings of like, this is like function f. Function f is in file y, and so maybe we'll say file f. This is, or we'll use file A, file B, file C. All of these files are in folder D, which also has a node, right? So maybe we draw D here for directory. What happens is for the first pass, we will render all 4 of these points, but we will tag them all as directory D. And that will kind of cause like each pixel to say, which node am I nearest to? Oh, all of these nodes are D. So I will tag my background with directory for each of these things. And then what we do is we go, okay, let's go one level up now and let's look at the files instead. So then we draw the same cones, A, B, and C. We don't draw the directory anymore because it's not part of this, but we tag them with like A, B, and C. And we render like on top of the thing that we already rendered before, right? So we'd render like smaller cones like this. Kind of hand wavy, right? Now, this is stupid because A, B, and C were like already part of the previous render. We're rendering the same cones multiple times. And so I think what I wanted to do here was, we know that like there's some threshold at which we want to stop considering B, the pixels part of B, and start considering them part of like the entire directory, right? And so you could kind of imagine that as you draw the cone once, right? And you kind of have like color bands on it, right? So anything up at this point, this is B, and anything below that is color D. This guy has a nice stash, not sure about the monocle though. Dude, we love seeing faces and everything, eh? You've got like but like what I'm considering here is that you could render one cone for all layers here, right? And so what this actually means is we already have to split up this cone into multiple segments, one for each layer. And what we could do as part of that is actually render these as separate pieces of geometry that are sorted front to back, right? That way we have this, that way this would also solve the problem of like, if rendering these like fat ass fucking cones that fill the screen over and over again is writing like way too much to the depth buffer, if we just render all of the top ones first, we don't have that problem because the top ones have like small radii, right? And so then we would only have to like look at the parts of these lower parts that weren't already covered by this. And so I bet that would have like a big speed up in like multiple ways, right? We would only have one draw call, and we wouldn't like, maybe we wouldn't over render the depth. But first we have to test that. We have to test our theory that rendering many large objects that overwrite the depth buffer will take a lot of time. That's what we want to prove right now. So let's look at that. So it is 3740, and let's prove that depth rewriting is slow AF. It's best to draw opaque objects from front to back. Yes. Yes. I think that I understand. But I want to prove that I want to prove that that is the problem that we're having right now, if that makes sense. So fuck all this cone stuff. Let's try to make a bare bones repro here. So maybe we'll call this like performance validation, say, or something. And in here we have some function. And in here, what do we want to do? We want to render plane at depth D. We want to kind of render many planes, I guess. Let's say like render 1000 full screen planes sorted back to front. No fragment shader. That's what we want to do. So let's open BuildZig, who renders this thing, and we will pull in our like all of our little libraries to use with this guy, and we'll call this a performance test. Okay. And all of these guys, everywhere that says like Voronoi test goes to performance test. Okay. Is that what we called it? Performance test? Performance validation. Performance test, performance validation. Okay. I guess we need to go into that like main performance validation, and let's just start by returning error. Oh no. Sadly, the only profiler that can still profile OpenGL seems to be NVIDIA Insight. I think I saw an AMD profiler. I just couldn't get it to work on NICs, so we'll work with what my dumbass has found. Okay, this is returning oh no, which is good. Have you verified if it's GPU bound or CPU bound? I'm like 95% sure it's GPU bound because like the CPU is not. I've like reproduced this in like cases where the CPU is like basically doing nothing. Okay, so let's I guess pull in like the GLW stuff from here. We need to get our main loop going, so we'll just kind of copy I guess all of this. This is all GLW window initialization stuff. You could argue that this should be a library at this point. This is coming up enough that it's like fucking annoying to do this every time, but you know, I would agree. Okay, so we initialize our window like this, and then we do our render loop. We do our render loop where we keep this thing closed, we clear some colors. I guess we should also make sure to enable all the same OpenGL features here to just for a fair comparison. And then I guess we'll just start with like a GL clear with red just to make sure that our shit's up and running. Okay. So this should give us a red window. Not quite, because we probably forgot to call GLFW swap buffers, and we also have to clear our input queue. Or else we'll ourselves. Okay. So that should give us a red window. There we go. Red window. Okay. And so now we want to like construct some planes. So let's use, I think we have this like how do I want to do this? Compile link program that takes in some vertex shader and some fragment shader. I guess makes sense here. I guess this should happen outside of the render loop. And this thing gets deinitted later, probably. I guess we need some sort of like vertex shader and fragment shader. So we'll say test vertex shader is equal to, I don't know, like you have to like specify the version in here, right? Can we just like copy these shaders? And I guess we don't even need a fragment shader. We were talking about that. We only want a vertex shader. And so in here, I guess, can we just do this based off like vertex ID? Hopefully, yeah. Right, we should be able to go like let's ask like some idiot some AI idiot. We can ask for like can you write me a vertex shader that renders a triangle based off GL vertex ID or something? It's something like this. So he defines 3 positions and then he uses positions GL vertex ID like this to set GL position. And that seems reasonable to me. Seems reasonable to me. So this is test vertex shader, and we kind of just do whatever the fuck this idiot said. Okay. Did we forget this has to go here as well? And then all of this stuff needs to get indented. And then I guess all this stuff can go back by 1. Here we go. Okay. Okay. So we have some points. Don't give a fuck about the colors here. We set the position, no vertex color out. And we need to define like a layout, right? Where's this like layout qualifiers? Just out. Sure, so we don't have any inputs or outputs here. Sure, okay. So we should be able to be like, we should be able to just be like, I guess for completeness, just for like proof of concept, let's actually make a fragment shader that just renders white. What is it? Out vec for fragment something, and we go like fragment was equal to vec4 1.0, 1.0, 1.0, 1.0. Then here we use that test fs, and this is actually supposed to be like gl dot what, like delete program or something? Program, free program, remove program, delete. I thought it was delete program. How do we function? Yeah, GL. Oh, GL delete program. I forgot. Okay. Okay. C import has no. Oh. Okay. This maybe? There we go. Nice. Okay. So then we try to draw some arrays with that thing. So we have triangles that we want to draw. And we want to draw the first one. We have 3 vertices to draw. That is not doing what we wanted, so we did something fucking stupid. First of all, can we like put like a syntax error in here just to make sure that like something, okay, that's good. Now the question is why is this not drawing our fucking triangle? I thought this would do it. So let's just double check here. So we have GL position. These are reasonable vertices. Yep. These are all reasonable. And so why the fuck is this not drawing anything? We could render dock it. That'd be kind of fun. Now that we have the ability to do this because we're streaming under X. It's pretty hype. Okay, so we can actually, wow, debug. Wow, draw arrays. So this does not help us at all, huh? Oh, is this one of those things where we like need a vertex array bound or something? I seem to remember that coming up before. Vertex array. Gen. I seem to remember this coming up. Oh, we're also not using the program. That's probably a bigger offender here. Okay. So can we double? Oh, here we go. Here we go. That's a fucking triangle. So I don't know why it's not showing up here, but at the very least it's showing up in render doc. I wonder if it's like, is our vertex? I mean, I do remember like having trouble with this before, where we have to actually bind a vertex array. Like something like this. Bind vertex array. I seem to remember this, but yeah, okay, yeah. Okay, sick. So we have a triangle. We are drawing the triangle, and render doc probably making a vow when it recreates the scene. Yeah, that makes sense. I that would be reasonable because it has to render the shit somewhere. Okay, so we can draw a triangle now, which means that we should be able to adjust this now to change the z position based off the vertex ID, right? So I assume that if we do like a depth, I don't need these comments. Can we do like depth is equal to GL vertex ID over 3? So this is like, I guess this is like index. And then we do like float depth is equal to index over 100 or something, right? Just to get in the range 0 to 1. Sure. And then we can do like depth here, and then we probably need to do like float here and 100.0 here or something. Something like that. And then can we actually get a little tricky here and say like out float depth here, take the depth in here? Or can we access just the depth buffer from fragment shader? I just want to see if we're rendering like something that's like far away or close, you know? GL fragcore.z. Yeah, that seems reasonable. Seems reasonable, so we don't even have to pass anything. We can just use can we just use this as like blue or something? Fuck. What's it pissed about? He's mad about like syntax error at line 9 or something. Oh, probably here he doesn't like this. Is it the other way? Float like this language? IDX used uninitialized. Why? Vertex ID has a capital D in it, right? Okay. And now he's drawing nothing, which is not good. Why? Index should be like 0, right? We should only be seeing index 0. Right? Oh, which he's just not liking? Was this... Oh! Oh, because I'm using this in the wrong fucking place. Oops. These should be vec2s here. And then we should be using the depth value here with a homogeneous coordinate of 1. I forgot these are 4-dimensional vectors. That's confusing. Now he's mad because this thing needs a vec2 everywhere here. Okay, there we go. So now this guy is like kind of yellowy. And I guess if we start drawing, I guess we probably want this to be negative depth so that as we move up towards our face, these things get like brighter and brighter and brighter. And then maybe here we do 1.0 plus or something. So this is going to become like, this is going to like work towards -1. So I think we just want this to be negative here. Okay, so this is like yellow, and then if we crank up the number of triangles that we're going to draw, does this thing get like brighter? Is like all I want. Who fucking, I can't tell. I don't see like more blue in that, which means that we might be doing this wrong. We might be doing this wrong. Fuck. Thinking. So index get bigger over time. Depth get bigger over time. Into the realm of like 3.0, right? Or into the realm of 100. This will eventually get to 1 because we wrote 300 here. 300 over 3 is 100. 100 over 100 is 1. So this should get towards 1. And there's no depth testing right now, I think. So it should just draw all of them. Okay, so we do eventually get the white triangle here, so that's good. But we want it to be negative, right? Yeah. Oh, which means this thing gets scaled not 0 to 1, but to like some fucked up number. I forgot about that. Right? This is in like window coordinates where you have like 0 to infinity instead of -1 to 1. So can we actually just pass depth along? Does that make our lives easier? Out float depth here. In float depth, and we use depth here instead. And then can we render like 3 triangles to get the first one? No? I want this to be fucking white, man. I want this to be white. Oh, we didn't pass along depth here? Also, I'm surprised this compiles. Fuck. God damn it. Okay, but keeping it, maybe we'll just allow whatever the fuck we did a second ago. Kind of worked, I think. So this was white, and then we drew one of these, and it was yellow. Yeah, okay. HOA is talking about their neighborhood. God damn it. I guess we can just use the depth testing function of greater, and then that just solves our problem. That just makes our lives easier. Okay, sure, let's do that. Okay, so now what we want to do is we want to benchmark what happens if we draw like 3,000 of these things, right? We want to see, and we want these guys to be like big. So can we change these like to 1.0 everywhere it says 0.5 here? Okay, so we're drawing 1,000 triangles that fill the screen. And we want to see, does RenderDoc have the same shit where it's like, holy shit, that's expensive, right? That's what we want to find out. So we close this, we go here, and we look at the durations, and that's a really good sign that this is approximately the same expense. We're seeing that 4 milliseconds. We were seeing 5 milliseconds with the cones, but 4 milliseconds, it's about the same, okay? And now we want to see what happens if we make sure that we only draw one of these things instead. So can we like enable, I think it's GL depth test. And I think we see something like GL depth func. And this thing is getting larger. So we want GL greater. And we should see pretty much the same behavior. Oops. Maybe less. Let's try that. Still no good? That's not good. Oh, because we're not clearing the depth. Clear depth, and so if we want to start this thing at 0. Okay. Okay, so we're seeing this guy still. And if we change this to GL less than, and put this to 1.0, we should see the yellow one. Okay, good. Okay, so in this case now, if we rerun this in RenderDoc, is this like way fucking faster? Yes, it is. Okay, that's a really good sign. Now, oh, I've seen this before. RenderDoc does this like weird shit where it doesn't seem to correctly render the textures in these stages if I don't have a texture bound. I don't know why, but we can just do like, we can just make a texture here, bind it, and then I think that fixes that problem. I think it's actually already bound after this. So I think we just go like this. And if we rerun this thing in RenderDoc, I think that fixes that weird fucking bullshit. Dude, I had to bisect so hard to find that problem. Yeah, this looks like way better. Way better. Okay. So can we now disable the fragment shader because we're fairly confident that we're doing what we want to do now. So we take this test fragment shader, we say null here, and we do the same shit now. We build it, we rerun it. Oh, we also have to disable the, what was it? It was like GL color mask was GL false a bunch of times. Something like this. Okay, run it again. Yeah, okay, color not made. And now we're seeing that when he draws this thing, color buffer undefined, buffer, depth buffer here, and then we go back to rendering the other direction. So we say GL greater, render from 0 onwards. And we're hoping, well, hoping is strong, we are expecting to see that this is slow as shit because we are rendering the same fucking triangle to the depth buffer only over and over and over and over and over again. And that's slow as shit. Okay, so we see nothing on the screen. We capture the frame. We hit this button. No. Whoa. Okay. That's interesting. That's interesting. So if we re-enable the fragment shader here, does it go back to being slow? Because if so, that's kind of crazy. Okay, so this is slow again, 4 milliseconds. And then let's just like really double confirm that we're not crazy. Build again. Launch. No. Capture. Close. Oops. Times. Not slow. Okay, so this is a clue that our guess was wrong. Right? Does RenderDoc show you like insight when you're missing required GL calls and you get them in the wrong order? I don't know. I'm not 100. I don't really know RenderDoc very well. I only got it working the other day. Why is screen black in this test? Because we are intentionally trying to do a depth only pass. Right? We are intentionally not writing out the color buffer to prove to ourselves that it is writing the depth that is slow. And I now do not believe that that's the case because of the fact that this test, just by disabling the color buffer, we go down from like 4 milliseconds down to 300 microseconds, which is not the behavior that we saw in our cone rendering test. So I guess the question now is like, why are these different? Right? Because our suspicion was a big cone covering the screen rendered into the depth buffer over and over and over again was causing problems. And that does not seem to be the case. It could be that OpenGL might have found out. It might be doing something like, or like the graphics card, someone might be doing something intentional, something where how do I say this? It knows that the whole triangle is occluded? Maybe? Right? Is that a possibility? The reason it's slow is that you can't do the depth-based early out fragment discard when running back to front. That doesn't make sense to me. Thinking. Why? So why not? Okay, sorry. Yes, you were correct. You cannot do the depth-based early out fragment discard when running back to front. Sure. But then why, when we do a depth only pass of our cone situation, is the behavior different than we do a depth only pass of this triangle situation, right? Because we found when we rendered our other program, Viz, with, we need to get the right working directory and shit here, with res samples svimp full. I think this is the guy. This is doing the same shit. Right? We have the fucking frame disabled. We have no output like color buffer, but we are trying to render depth. And rendering this depth by itself, no color output, as far as I'm aware, is equally slow. Adding color to this has almost no noticeable effect, which is different than our triangle case. So our theory here was that big thing render over whole screen slow to depth buffer. And that's not, we cannot prove that yet. So my next guess here is that it's related to the fact that some of the cone always peeks through. That's my next guess. So can we trigger that case? What if we rotate the triangle a little bit every time? maybe? Or we give it like a slant so that like part of it always peeks through. Yeah, you could do. I think that if we render the triangle kind of Mr. Monocle Man, like so that this corner here is like pointed up out of the camera. I can't really draw that, but you know, kind of like this way. And then we could also rotate it a little bit. That way, it's guaranteed that this corner will always be in like a new position, and we should always have to render at the very least part of the triangle, even if the part that is visible is kind of slow. Um, or we could rotate it out of the screen a little bit. So we could kind of like, instead of rotating it this way, we just keep rotating it like so that this corner gets higher and higher and higher and higher and higher. I think that's kind of better. Yeah, let's do that. Oops. Sorry, I wasn't here from the beginning, but the slowness could just be caused by overdraw. Like if you have a situation where the depth test always fails, you'd expect it to be slow. I agree, but I do not expect it to be this slow. Like, this is what we are rendering, right? Essentially this. And what we are seeing is like a 5 millisecond render. It just feels too long. It feels too long. And my thought here is that it's related to the fact that we draw these cones in order. Each cone take up big amount of space. Wait, why did, and so my thought was in a depth only render, this is still slow. And so if that's slow, how come rendering a triangle that fills the screen that gets closer and closer and closer and closer to us in a depth only pass is not slow? What is the difference between those two? I don't know. And so I suspect that either we were wrong when we rendered this, and it's not a depth only pass like we thought it was, or there's something about like partial exposure of the cone, right? Every cone that we render is definitely partially exposed. Every triangle that we render is partially exposed. And so I wonder if there's a difference there. And so that's what I wanted to check here. That was the next thing I wanted to check. So what do we call this thing? Performance validation? All we have to do to check that is take the X position or the depth position, and if like depth plus equals, if like index over 3, index mod 3 is equal to 0, we increment this by some extra amount. Oh yeah, you guys were talking about the render doc overdraw thing, huh? That does seem kind of nice. How do we see that? Overlay, overdraw. I don't know if white is good or bad here. Can we launch our other thing? What's our other guy? Performance validation, launch, no. Capture. Uh, this is not looking how I want. Okay. This, I do not know what this means. Should tell you how many layers on mouse hover. So this tells me 100 overdraws here, despite the fact that this is running fast, right? We're saying 101, 101 here. I assume that if we kind of bring this guy back down to kind of intentionally going the right direction, we should see very few overdraws. I think. Let's just double check that. Launch. No. Fuck, he's mad because we fucked up our... We started modifying our vertex shader. Let's go back. Let's go back. Launch. Capture. Here. We go back to the depth buffer and we go to overdraw here. This does say 100 here still. Which is kind of interesting. Not sure. Not sure. There is also a way to query overdraw, actually. I think I saw that somewhere. You can like query it from OpenGL itself. This is like overdraw query OpenGL or something. Or occlusion calling OpenGL or something. Occlusion. Ah, fuck. OpenGL wiki occlusion, maybe. Yeah, occlusion query was another thing in here that we could look at, maybe, which tells how many samples pass the depth check. Okay. Anyways, I want to go back to what this thing I wanted to do, which was pull the front of the fucking triangle up a little bit. So we just say depth plus equals 0.01 here. Yeah. So just one of the indices pulls a little bit up more. And I guess we want to pull it up not just by a fixed amount, but by some like scale of vertex ID. So can we just like square it? Something like this. Okay. So what are we trying to test here? We were trying to test if this is still, if this gets slower by doing that. So first of all, do we see any difference in the depth as we get over there? No. Maybe because we drew this the wrong way. Maybe this is to be depth. We're using less testing. So maybe this is supposed to be minus. Maybe we're supposed to get smaller here. Oh, I need to think hard about this. Can we do this with greater? Does that make our lives easier? So here, depth is going up with number. We need to invert that. Maybe we just do times -1 here. That way it'll get closer and closer to us as the other stuff gets farther and farther. Yeah, that sounds right. That sounds right. Okay, so let's try to look at the depth that came out of this thing. And we are seeing depth 0.005 everywhere, which is not great. This is not what I wanted to see at all, huh? Which means that we've done something wrong. Okay, let's start with only drawing one triangle instead of 1,000. Launch, no. Capture, close. Right click here. 0.5 at the top. 0.5 at the bottom. So what am I high? Oh, because we took that shit out. I'm dumb as bricks, dude. Okay. So we draw one triangle. We're like, yo, take the first. Oh, this is supposed to be GL vertex ID. That explains that. So take the first vertex, which is the bottom left one. I guess I want it to be the top one. So let's see if this is 2. Bring it closer to us. That's what I'm trying to say. That's all we're trying to say. Bring the top one closer, baby. So we go back here, click on this. I don't like that it feels like the depth is like consistent everywhere. You know what I mean? It's like, it says 0.5 here, and here, and here, which is like, why? What am I doing wrong then? What am I doing wrong? Like, if I just type 100 here, does that do anything? Am I like fucking high and we're just doing the wrong thing? Could be, you never know. You never know. Yeah, so everything here still says depth 0.5, which means I must be high out of my mind. Why is this not change? I don't understand why this doesn't change anything. Maybe the depth, maybe this never triggers? It has to. This has to trigger. Index is always 0, right? Yeah. Oh, yeah, good point. Good point. Sorry. Yeah, good point. So if we do 2 triangles, then we should see something different because it should be 1. Good eye. Good eye. Okay. There we go. Okay, so this is what I wanted to see. So this stuff now has depth lower. This has depth that's close to what we had before. And then we want to like kind of lower the amount of this thing. So can we just do like -1 here? And what we should see is as we get farther up the stack of things, that top guy should come closer and closer and closer and closer. So here we should see that this is 0.49 and we have 0.50 at the bottom here. And then we start rendering like 1,000 of these. And that guy should be like in our fucking faces. Right, so now we go back here, we look at this, and this guy's, oh, they get kind of clamped down to 0, which isn't good. Which is not good. So we probably want to lower the amount that it's kind of shifting itself up. We might want to do 1,000 of these, over 1,000 here, and then does that kind of fix itself? Launch? No. Okay. Capture? Okay. Now we look. So this is depth just around 0 to just around 0.5 at the bottom. Sure. We check how long this took. That took a very long time. Interestingly, like 8.9 milliseconds. And if we just disable this part now, we should go back. Do we go back down to 4 milliseconds or whatever? Bump, 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 bump. Oh yeah, so we're down to like 3 milliseconds now, which is interesting. I guess I'm a little concerned here that we've got the order of GL less, GL greater wrong here. So let's just, we just have to be very careful here because we don't want to draw incorrect conclusions. So we are saying GL depth func, GL less. We are starting with a clear color of 1. Our depth is getting bigger. So we're the wrong way. This is supposed to be GL greater. If we want to... yeah, we've done something stupid here. GL greater. GL less. Okay, GL less says we start with all depths at 1.0. We draw the first thing that is closer to us. So that's drawing front to back. But we're drawing front to back with the front of the thing coming up and up and up in the opposite direction. Yes, so that is consistent. That's actually super consistent. Half of one of your 60 FPS frame buffer to draw 1,000 triangles seems very sus. Did I do that math right? That's exactly what I'm complaining about, dude. That's my point. That's what I'm saying. That seems sus as fuck. Okay, so I think this is I think that this is doing everything that I wanted it to. What? No, not anymore. Now I'm confused again. Did I comment something else? Yeah, I did. Okay, so this was without like the depth hacking of the front thing. So this is, so this should be really fast. Is this not the fast case? right? This was the case where we have everything initialized to 1.0. Our depth is going up. Oh, I guess this was 100 before, not 1,000. Does that change anything here? Yeah, okay. I see. Okay. Sorry. Let's just super clarify what case we're in here. We are in the case where the depth buffer starts at 1.0. Then we draw one triangle with a depth of 0.0. This is less than 1.0, so it is drawn. Then we draw one with 0.001, not drawn. 0.002, not drawn. 0.003, not drawn. Right? That is the case that we're in right now, which is why the depth buffer in this case has a depth of 0.5 because it's normalized from -1 to 1 to 0 to infinity. So this is like the 0 case, right? Chill. Now, if we change this over 100 to over 1,000, because we're drawing 1,000 triangles and we want to make sure that the depth never exceeds 1,000, without doing any of that like weird shit, we go back. I think that we saw a huge performance degradation there. Yeah, we 10x'd our render time, which actually makes sense, right? Because we have 10x the number of instances. So I think I was wrong earlier when we said this is not a problem with the triangles rendering to the depth buffer. I think it's because I was only rendering the first 100 triangles by mistake. Because the other 900 triangles ended up past the view for estimate. I just didn't fucking notice. Now, what's interesting here is the problem gets even fucking worse if we enable this line that says bring that front corner closer to us every time. So that means that most of the triangle will end up behind the first one that was drawn, but some of it will end up above. And so that just gets even fucking worse because now not only do we have to do comparison with the depth buffer, but we also have to fucking write to it every time. Right? I think that's what we're seeing here. I think. So we capture. This goes up from like 2 milliseconds to 8. Yes. Okay, and we look at the depth buffer and we see that this front side, this top side is getting up and up and up and up. Bottom side is going down and down and down and down. Or, yeah. So this never gets updated at the very bottom after the first one, but all of these pixels above get updated some amount of times. Okay. Oh, I guess what's happening here, yeah, I think that's right. Okay, so I am now fairly convinced that just by comparing the full screen object, like something that covers the full screen, just by comparing that with the existing depth buffer, it is already causing issues. That gets down to like 3 milliseconds. Which is not great. So then the question is there a fix for that? So here we've actually kind of not proven this, and the question now is just like even drawing something below the existing depth is too slow. You're discovering why people do CPU side occlusion calling before submitting draw calls. That makes sense. That does make sense, except for the case. Now, the problem here is that we can't do that because every single triangle that we're drawing here is partially visible. So there's actually no occlusion culling for us to do at this point. So the question now becomes, is there a way to hack this in some way? We talked earlier about the fact that we could kind of do partial cones, right? So we could kind of like render them in segments like a Christmas tree. And I guess I mean, we could also do low res depth pass, right? Let's think for a second. So A low res depth pass doesn't help us at all. I don't think, because it just makes the crispiness of the Voronoi lower. Arguably, our Voronoi does not have to be very crispy though. Because our final goal for these backgrounds are to be kind of like masks for some shader that will kind of make the background look like galaxy wallpaper type shit, right? Um right, like we're planning on using it, oh fuck off, as a mask for something. Fuck you, fuck you, fuck you. Oh my god, I fucking hate the fuck. Okay, what about this one? Can we click on this? Oh my god. Okay. We're just trying, we want to use it as a mask to do some sort of like wispy thing like this in the background, right? So if the edges of the mask aren't very crisp, that's probably okay. Gotta split the triangles. So I don't know if does splitting the triangles help us? We could do like CPU side occlusion culling based off that, but I bet you that that would still be slow. Hand wavy. That's just like a guess. I'm very surprised. Oh, but I guess. Hold on. If your triangles were all smaller, okay? If our triangles had like cuts in them, oh, we can't loop cut this thing. Let's make like a. Can I open a new Blender instance? Okay, so we kill this stuff, make a cone, mesh, cone, right? If our, oh really, we can't loop cut this either. Okay, we can. It's easier. This is still doable. Mesh cylinder. We make a cylinder. We take the top of the cylinder and scale it down to 0 so that it looks like a cone. Okay, and then we can now loop cut these. Yeah. So if we did this, right, where like we have kind of like, can I turn off the? Yeah. We could then maybe have full triangles. We could like fully delete portions of the cone that are hidden based off of a low res depth test. However, then we would need to generate mesh geometry for every single cone with the occlusion called already, which kind of sucks. Can you explain the cone part? I came in late. Why is there any overlap in a 2D Voronoi drawing? Oh, here. We can just show it here. This is how we are generating the Voronoi. We originally, the idea was that you can leverage the GPU's 3D pipeline to calculate distance to point for us. Now, it turns out that that is not that fast, but I don't know how much slower it would be than doing this just on the CPU. Right? Like, because like the other option, if you have like 1,000 points and you're saying for each pixel which one is the closest, you have to do like, you have to search every point and do a distance calculation for every pixel, I think, or you have to use some sort of like intelligent tree structure to say like which points are like local to me, which we didn't want to make. So we're just like, fuck it, we'll throw some cones at the GPU. The GPU generates the Voronoi for me. I guess we should prove to ourselves that RenderDoc is not lying to us. There is a chance here, I guess, that its recreation is not faithful to what is happening in our actual program. So before we kind of make strong conclusions out of this thing, let's see what happens if we uncap our FPS and run the program with just looking at the FPS counter. So let's just see if these two things are consistent. So we run this thing. He says, yo, you're running at 1,300 FPS. Okay, that's what he's saying. 1,300. ish. 1300, 1400, 1300. So if we say this is 2 milliseconds, which seems way too high. What am I trying to do here? So if we have 1 over 1300, we should be seeing literally like 700 microseconds. No, sorry. Yeah, 1300 frames per second is 1 over 1300 render time. So I'm not really convinced that this is accurate. That's kind of interesting. Can we turn back on this, like, bring the front corner on top shit? And then rerun it again. Does that have, like, major FPS implications? That does drop us from 1300 FPS down to 400. So there is maybe truth in RenderDoc's like relative frame times, but maybe not necessarily in its like actual raw frame times. So there is a non-zero chance, I guess one, that we've drawn incorrect conclusions about the speed of the depth-only render of the Voronoi. Let's test that. Viz zig. So in here, can we check our frame times? Let's just double check that everything is the way it should be. So we'll turn back on the color mask and run this. Okay, so we had Viz launch. So this is not good. He is rendering white, and that's probably because we left on the node Voronoi stuff. Probably is not rendering with the correct fragment shader. Okay, so let's turn that back on. Render again. Now it's red. Why? Are we rendering? Did we hack this? No. Oh, here, distance threshold. Probably this needs to come back to the way it was. Render doc. Run it again. I'm trying to get back to the correct. Okay, there we go. So this says 69 millisecond frame times. 69 millisecond frame times. Now we want to see what happens if we do our depth only pass here to make sure that we have correctly identified this. Okay. Fuck, I already forgot what the frame time was though. We should write it down. It was 69 and I forgot, really? It's pretty funny. It was 69 milliseconds. Okay, 69 milliseconds. Okay, so let's turn back on, like, disabling of the color mask and disable the fragment shader again in our Voronoi thing. Okay, so that was here. And run it again. Yeah, we're still at 69 milliseconds. So it does, oh, and then now let's make sure that let's look at the contents of this thing. Yeah, so in the cone case, it does look like we're in the same state where... Oh, no, wait, hold on. Hold on. I think that we forgot to set the swap interval here. Yeah, we're still not letting it go to its full potential. Not letting it go to its full potential. Try again. There's so many things that we can get wrong here. Fuck, dude. Okay, so we'll go back to... Delete this 69 milliseconds. Fuck that. That's not useful. And we'll go back to rendering everything correctly. So full color. And let's only do one iteration. And then we have to re-enable the fragment shader in here. Okay, good, good. Everyone's happy. Load last settings, launch. Okay. 7 millisecond frame time, 6 milliseconds a second. So we're gonna say like 6 to 7 milliseconds. And then all we wanted to do was check if it's the same or better or worse if we do our depth only pass. Because we were not sure. Boom, 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 boom. It was this one. Boom. Boom, 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 boom. Okay, launch. I think we were seeing the same thing, 6 to 7 milliseconds. And can we trust render doc here? So if we're seeing 6 to 7 millisecond frame time, he's saying around 6 seconds here. So I think that in this case, he's kind of accurate. Okay. And I forget what the results of our test were about that triangle bringing the front corner forward. Did that have a major effect as well? Did that have a major effect? So here we are bringing the front corner forward. We are bringing the front corner forwards. We have to remember. We have to remember. So front corner forwards 2 milliseconds. And then we disable this part, run it again. Launch. Oh, wait. No front corner forwards. 0.71 milliseconds. Okay. So this indicates to me that we should be able to gain render speed by not rendering the full cone. I'm back to thinking that. I'm new here. Can I know what you're building? Yeah, we're building a code visualizer. It's supposed to look kind of like a map of the stars. The idea here is that like as we work on a large project, we put like points in this graph around, and we like highlight the components that are related to what we're working on right this second. So like if we're working on like the GUI framework, we're gonna have like in the text box, we might say, okay, text box is related to label, is related to text renderer, but the rest of this code base, don't really worry about it for today. And we are kind of debugging our slow OpenGL today. Is this debugger release build? Debug, but I don't think it matters if like we're rendering, if we're like talking about like GPU rendering speed. I do not think that compiling optimizations on the CPU side makes a difference. I could be wrong there, but I don't think it really matters that much. I guess in this scenario, if we're rendering full frame times, then it could, huh? Because we're doing a bunch of stuff on CPU between frames, which makes it an unfair comparison. Which means that here we should probably just like limit as much as we can. Yeah. Probably. So probably we should do like all of this stuff one time off rip here. Then do our render here in the main loop. Yeah. Yeah. That makes it a bit of a more fair comparison. Okay, we'll go back to running viz here. And what we should see is like one constant thing. So if we capture one frame here, we're seeing 1 millisecond, which is very good. And if we look at the depth buffer that came out of this thing, it's actually pretty sane. That's actually pretty sane. Okay. So I guess the result of all of this is that it's fine. I think that's what we just learned, right? So we remove all of the like real work and just do the render. We're at 4 milliseconds in render doc, but render doc's a fucking liar because we were seeing 1 millisecond frame times in our actual app. And at 1 millisecond, I'm not worried. I was worried at like 5 milliseconds, but now that I know that render doc is not accurate, and 1 millisecond for our whole thing is like just doesn't concern me at all. All right. Well, that was a fun stream. I think we did make one real fix here. Oh wait, hold on. Wait. I'm a fucking dumb piece of shit though. Let's go back to rendering the colors. Does that make a major difference? Because if it does, we still have work to do. I forgot. We should actually fucking look at what we're looking at. This is fun. There's so many mistakes to make. Where's our color? Oh, I didn't save this one. There's so many mistakes. So many mistakes. Okay, here we go. Yeah, I mean, this is still 1 millisecond. So we're just fucking chilling. We're actually just chilling. So I think we did make one real fix here. The one real fix that we made was this one. This change right here that used to say if depth is greater than distance threshold, discard. This was bad. This was very, very bad because this prevented the early depth testing. But with early depth testing working, I think everything is just kind of working the way we would expect. So this whole stream, this one stream was literally this line. This whole stream was this one line of code. But I think that we learned a lot along the way and got to play with a lot of stuff along the way. So I'm not really too choked about like the amount of like the time we spent here. I still think that there are we could still do that trick to render one layer, like only one layer, but it seems like we probably won't have to. So cool. Interesting that you multi-line string literal for your shader code. I normally embed file them. Yeah, I mean, it's just because I'm too lazy, dude. I mean, you're right. It is nicer, but I just don't want it right now. Also, hello, Malag. Welcome. So I think we call it there. Thanks for watching, guys. I hope that you had fun. I think that this is the way it goes sometimes, right? This is the world of coding. Sometimes your assumptions are wrong and you question them and you eventually get to the point where you're like, oh, things were fine and I made a mistake. But that's part of the process. So I hope that it was fun to watch that. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 3:45 now. And so if you're watching live, you should expect to see us live between like 3 hours ago and now-ish. If you're watching live and you want to keep up with the project, but you're like, I can't watch all the time, there's a YouTube link in the Twitch description. The VODs go up here. So check that shit out if you want. We should be back tomorrow, hopefully back on track for something a little bit more productive. I want to work on trying to make the background of these Voronoi look a little bit more like this so that we have like our star map getting a little bit more star-like. But yeah, we'll be back tomorrow. So thanks for watching. YouTube, peace out. Twitch, let's find someone to raid.